Hey guys, in this tutorial I'm going to show you my method that I use for creating a site model from a bunch of contours that you have. Here's what the final result will look like, and we'll be starting with a set of contours which look like this. Alright, so I'm going to dive into a new document, get rid of this. I'm going to keep this base rectangle that I've created here, and I've also imported a set of contours into Rhino. And so these give you information about the sort of the rise and fall of the land, the shape, and all of these are at, I think these are at half-meter increments, so we can use this data to reconstruct the actual topology for the site that we're using. So we do this a lot in architecture. So cool, I'm going to go ahead and show you how to do it. So we're going to crack open Grasshopper, and we're going to drop down two curve components. The first one is going to be my rectangle, and then the second one is going to be all my contours, but not my rectangle. Cool. So then what I'm going to do is I'm just going to start off by doing a curve join, just in case there are some curves in here that aren't joined. So after the result, yep, we get 426 polylines. So we had what's that, 261 curves that were not joined. So that's helped me a little bit. Next thing I'm going to do is I'm going to project these curves that I've joined down to a base plane, in which I've probably used the wrong project. There's a couple of different project methods, and the one you want is this, that sort of has a sphere projecting down onto a flat plane. Cool. So I'm going to take this join, plug it in there, and key thing to note at this point also is that my rectangle that I've created also sits on the ground plane. That's important because what we're going to do, we'll get there first. So the other thing, the first step that I'm going to do here is I want to firstly check which curves intersect with this rectangle and which curves don't. And so for that I can go into my intersect tab, and I can go into this physical section, and I can do collision between one and many objects. So my object for collision is going to be, it doesn't matter which way we do it. I'll do it this way. So my rectangle is my object for collision. Okay, maybe it does. I'll do it the other way. Alright, so now we're getting a whole lot of true and false values. So I'm going to create a cull pattern. And oops, actually I need to use these projections, because that's the point of projecting it. If I don't project these curves to the plane, none of them are ever going to intersect this rectangle. But you can now see, okay, we do have a true value in there, which is a positive sign. So now I'm going to cull these projected items, and there we go. So this is now going to give us, actually I'll just go and turn this layer off in Rhino. This is going to give us any curve that intersects this rectangle. So I'm going to take that, and I am going to do a intersection. So I'm going to do my, I'm going to use a curve-curve intersection, and so my first curve is going to be the rectangle over here. My second curve is, or my second set of curves is going to be all these flat curves, and that's going to give me all the points that they intersect along here, and I'm going to use that to split these curves up into smaller sections. And the way we do that is with what's called a shatter. And what we can in fact do is we don't need to use our projected curves on the shadow. We can in fact use joined curves, the ones that are in their actual position, and we can shadow them at this this output here is our T stands for parameter. So our parameter on our B curve, because we want to split the list of curves coming in here, oh wait, hold on. I did overlook one thing. When you do this curve intersection, it's going to basically insert like a layer of grafting. So at the moment this is going to split every curve 408 times. What we want is to graft this input here as well. And then there we go. That process, if I'd left it, would have probably taken a few minutes. Instead it only took about 10 seconds. Actually, we can turn on, for this script, I'm going to turn on my profiler, because that's going to tell me how long everything's taking, which is quite useful. So that took 4.6 seconds. Alright, so I've shaded that now, and now I need to test which curves are inside this rectangle and which curves are outside it. And the way I can do that is with an inclusion test. We go to curve analysis, we have this point in curve. So for that we need a point, and so what I'm going to do in order to get a point is I'm going to evaluate the curve. I'm just going to go and grab it because apparently I can't spell very well. Let's see, evaluate curve is right over here. So I'm going to take all of those curves, I'm going to reparameterize them, and I'm going to set my parameter value to 0.5. So now we're just going to check whether or not these values are in fact inside our curve, inside our rectangle. Okay, so this is the point I'm testing for inclusion. This is the curve I'm testing against. And then it's going to give me three numbers, either a 0, a 1, or a 2. So 0 or 1 we don't care about, but if it's a 2, it's inside the rectangle, so we want to keep that. So I'm going to create an expression, which is going to be if, open parentheses, x equals 2, then our true condition and our false condition. That is how you set up a conditional statement. So you have your if, then your open parentheses, this is my condition, so if x equals 2, then return true. If it returns 0, 1, or anything else, return false. Cool. So now, plug that in there. I'm going to get rid of the y because that we don't need that. And now, I should be able to run these curves over here from my shatter through this cull pattern. Ooh, that's what have we done there? Whoops, it looks like I may have used the wrong curve for this shadow. What I actually wanted to do was shadow my projected curves. And so now, let's see what we've got. Wait, hold on, I did the wrong one again. I wanted to shadow the curves coming out of this cull pattern. And actually, what I do need to do is, let's see, I need to make another cull pattern because I want to get these joined curves back. Alright, so the curves that are in their correct Z position. Alright, so third time lucky. There we go. It's taking its time. There we go, 6.7 seconds. But we should now have the correct result. Turn these off, and there we go. We've got our curves constrained to this rectangle. And now I need to get the rest of the curves. So we tested whether these curves collide with the rectangle or not. And so now we're going to use a NOT gate. And so this NOT gate flips our true and false value. So where we were testing for a collision, now anything that does not collide is going to be true. So I'm going to use a cull pattern again, and I'm going to make sure that I select the right thing this time. It's my joined curves, and here's my pattern. Okay, so you can see it's giving me a whole lot of curves inside here, but it's also giving me a couple outside, because as we might expect, these ones do not intersect with this rectangle. So we can just do what we did over here again. We can actually just quite literally copy and paste these 4 components. And so I'm just going to lock the solver really quickly just in case. We're going to evaluate all of these curves, and then we're also going to cull. I'm also going to plug that into our cull result, and when we unlock the solver and deselect and hide this cull, there we go, we should now get all the curves inside this rectangle. And so this is everything we need to now create the next step. In order to turn this into a site, or into a site model, we need to use what's called the delaunay mesh component. Now, the delaunay mesh component uses a mathematical algorithm called the delaunay algorithm, which is a triangulation method. It basically looks at a group of points, and it joins up the closest ones to each other so that they don't form weird intersections. Basically, it's a really good method for creating meshes. You also have the optional input of a plane. So if you wanted to, we're going to create the delaunay mesh in the world XY plane. So we don't need to plug anything in. But if you were working on a vertical site model for whatever reason, you'd just plug in either a YZ or an XZ plane, and it would work exactly the same. Right, so now we need a collection of points to plug into our delaunay. So what we're going to do is we are going to divide our curves, but we're not going to do a divide curve, because the divide curve is only useful if it's only useful if we are dividing sort of if we want an equal number of points on each curve. I guess there are ways around that, but it is a bit easier to just use the divide distance. So we're going to take all of these curves and all of these curves. We're going to flatten this input, and actually I don't need to flatten it just yet. I need to set a distance between points. Now before I do that, I just want to check what sort of distance I want. So I'm just going to draw a cheeky little line on the side over here, and if I wanted my points to be this far apart, that would be about 20 mil. I need to plug a value of 20 into a slider, and we can see that number right down here. If you just look over here, drag it to about there, and that's about 20 millimeters. So maybe I'll do a little bit less than that, but always make sure you do that when you're doing this divide distance, because if I were to plug in 0.25 here, it is going to give me an insane amount of points, and it'll take far too long to process. So I'm going to set this to a maximum value of 20, and in fact I'll set the value to 20, and then the divide distance is going to take some time. This will take a few seconds, and then it'll spit out a collection of points at regular intervals along all of these curves. And then we're going to plug that into our points for our delaunay mesh algorithm. Just give it a few more seconds. There we go. So now I can turn these off, and I'm going to plug my points in here. Oops, I also need to, I need to flatten the list of points. And that'll take a little more time as well. Whenever you're ready, Grasshopper. Cool. There we go. So now we've got our mesh sort of realized. We could go into perspective view and we could see, there we go, there's our representation of the site model. For anyone interested, this is a model of Mount Eden, which is a reasonably famous landmark in New Zealand. Alright, so I've done my delaunay. At this point I might just add in a few sort of, how should we say, a few sort of workarounds, because you can see my mesh is not going right to the edge. So actually what I will do, just for purposes of creating a proper good mesh result, I will show you how we can fix this. We will in fact use the divide curve component, and what we're going to do is we're going to get the length of each and every curve. So I'm going to flatten this. Actually, I'll put it into a curve input first. I'll flatten that, and then I'm going to, let's see, so based on the length, what I'm going to do is I'm going to do a division. So I'm going to divide the length by this number, and that's going to tell me how many divisions I'm going to have per curve. And then I'm going to plug that into my number of curves, and I'm going to plug my collection of curves into here. Once again, we'll get our list of points, but now we'll get a nice sort of, how should we say, well, we'll get a collection of points right along the border. And we're also going to need to insert all of these corners from my rectangle. So what I'm going to do is I'm going to explode this curve. That'll give me the 4 corners. And what I'm also going to do is I'm going to do a closest point, because at the moment if I were to add this point into the collection of points, it's going to create a weird mesh where we sort of have this weird triangle right at the perimeter. So I'm going to take these points and I'm going to flatten this output, and then we're just going to plug that into, actually I didn't want my, maybe I did. Yes, so that gives me this point. It tells me that this point over here is the closest point in the list. So what I'm going to do is I'm going to deconstruct that point. I'm also going to deconstruct these points, and then I'm going to reconstruct the point with this as my z value and these as my x and y's, and there we go. Now we've got a corner point as well. So now I can preview all of this off. I'm just going to lock my solver. I'm going to flatten the input coming in here, which is going to be my curve divisions and my constructed points. I'm also going to turn off anything else, and then we're going to unlock the solver. And there we go. Now we've got a nice delaunay mesh going on. And if I wanted to, actually I'll bump that up later, I won't do it just yet. We're going to keep working on this. So if you wanted, you could stop at this point. You do have a working mesh which gives you a pretty good representation of the site. But I'm going to take it a step further for sort of aesthetic sake. We are going to take this curve that we created over here. We're going to turn it into a surface. I've done a similar method to this before, so you may recognize it. We're going to take the dimensions of this surface, and we're going to divide u by v to give us a ratio. So this is the the size of u in relation to v. And so I'm going to multiply that by some integer. I'm going to create a slider with a value from 0 to 500. I'm going to plug that into my b. And so what this does is this is going to create really nice squares on our surface. Well, it's gonna approximate squares as best it can. So I believe this should be my u, and this should be my v, if I'm not mistaken. So we've got 840 and 983, and we have, yes, so this will be my u, and this will be my v. And we can check just how square we're getting. And you can see as we reduce that, we do get these pretty nice squares all across the mesh. I mean, they're not perfect squares, but this is a pretty good method, I feel. Alright, so I'll bump this up to maybe somewhere around 250. Now what we're going to do is we're going to project points. So we're going to project all of these points, which I'm also going to flatten. We're going to project them in a positive z direction, and we need a piece of geometry to project to, which is this delaunay mesh. And so now I should get a collection of points, which are all across this mesh. Oops, did not mean to disable that. And so now I can make a mesh from points. I'm going to plug my points in here, and I'm going to... Oh, actually, one thing I forgot to do. Sometimes you will get a weird rounding error over here. If you don't round before you plug this in, it won't necessarily correspond when we do our mesh from points. So I always like to put this through an integer over here. It won't have any sort of noticeable effect, other than your mesh from points will always work, and it'll never turn red for any sort of error. So we also need to create two expressions, u plus 1 and v plus 1. So this is our u value, and this is going to be our v. You need to do this anytime you're doing divisions across a surface, just because it's always going to create one more division than you might expect. Alright, cool. So now you're going to notice that we do get this weird sort of situation going on where our mesh is mostly correct. If I were to bake this out and take a look at it, yeah, I mean, that looks all good across there, except we are getting this absolutely bizarre issue going on. And the reason that's happening is because the perimeter of our mesh is it's not necessarily in line with this surface. Just something with the way the curves are divided and the delaunay mesh produces the triangulation result. This is always going to happen. You're going to get nulls partway through the list. So in order to work around this, what I do is I put a scale in here. So we're going to scale this original curve, and we're going to scale it by a very small amount. I'll give this a maximum value of 1.1 and a minimum value of 1. I also need to find the middle of this curve. I'm going to plug my center into here, and there we go. So what we're going to do is we're going to use this curve to do our whole sort of trimming result and mesh creation, and then, okay, let me just do that first. So what I'm going to quickly do is I'm going to lock the solver, because everything's going to break as soon as I disconnect and reconnect this. Okay, so I'm going to reconnect these into here, and then okay, so our scale is going to be doing all this grunt work of the beginning part of the definition, and then we're going to connect the original sized curve, because that's the region that we wanted, into our surface, so that we're projecting from this smaller mesh onto the slightly bigger mesh, meaning that we shouldn't get any sort of errors. So now I'm going to unlock the solver, and now we wait. So the reason why I like this method is that you'll see it produces a very clean looking mesh afterwards, which is, I mean, aside from anything, it's easier to work with. If you wanted, you could also, if you wanted, turn this into a NURBS surface as well. Instead of using the mesh from points, you could use the surface from points and just replace your U and V, or only your U. You only need the U value for the surface from points, and then that way, you could trim into your surface if you really wanted to, and it would just make your, if that's what you want to do, that would be a lot more versatile. So now I can bake this out, and you can see we aren't getting any of those weird sort of errors. We're getting a very good, consistent, quadrangular, quite pretty looking mesh, if I do say so myself. Now, like I said, there's nothing wrong with using the other one, but I always prefer to do this, just because a good topologically accurate mesh, well, for me, this is how I prefer to do it. So now a couple of things about this mesh. It's not very accurate at the moment because I set my distance to 20 over here. You sort of have two layers of accuracy with this definition. The first is this one, so I'm going to set this down to 8. Yeah, so, oh, pardon me. You have this first layer of resolution, which is how much the curves are being divided, and so that produces a sort of a base mesh for your delaunay. And then the second layer of resolution comes in when we do the division of the surface, and you can choose how many divisions you want across that. And I am going to go ahead and say beyond a certain point, increasing the divisions will not do anything. Like, don't think that if you set the divisions of your quad mesh insanely high, that automatically means you're going to get a ridiculously detailed mesh. You need to sort of balance off this parameter here, which is from the delaunay. So we can see our delaunay is now a lot denser. Still not that dense. I mean, I have gone a lot denser while doing these. I'm only going up to 8mm just because of the time constraints on this video. And so then we'll look at our mesh from points, and you know what, maybe I'll bump this up to 500, because why the heck not? I'm not actually sure what would be a good value for this at the moment, but now I can bake this out, and there we go. You may also be looking at this and thinking, oh, that looks like the mesh has done something a bit weird with these sort of ridges, but I can assure you that is just how Mount Eden looks. It has these weird sort of ridges along the side of the mountain, which are sort of a historical sort of reminder of how people inhabited the mountain. But that's a story for another day. Cool. This has been a tutorial on how to create a Grasshopper definition for making a site model. Hope you enjoyed it.